2 o'clock. Let's roll. It's fake time? Oh. What is time? All right. So thank you to those of you who showed up on the queue early this week. We actually had, a kind of a significant number of people on the queue Monday and or Tuesday, which I think bodes well for the queue status on Friday. So here's hoping it isn't cataclysmic, or catastrophic, I think is what I meant there. So we have another exam coming up next week. It's, I feel like, let's see, one of my goals for today, before I close my eyes, is to make sure that you have a list of topics. But just in case I fail, it's pretty much everything in lecture, everything up through today. MP-wise, it includes MP3. And labs-wise, it's through last week's lab, so it won't include this week's labs. So that's just the, the vocal description of the content of the programming exam starting next week. Okay? Was there a question? I saw somebody was waving at me. No? Oh, I know what it was. It was, oh, I'm here. Come sit by me. All right. The other thing I want to say is that we're still in the process of calibrating the best way to use the Lecture Helper software. So again, I'm sorry if I didn't get to your question, but I'm learning how to use it from my perspective. So please use the software. The link is right there. I actually think that you will have opportunity to use it today. Now, just because Lecture Helper exists doesn't mean you can't also, or alternatively, raise your hand to ask a question. I will still answer raised hand questions. There is no barrier between us. For example, yes, what would you like to ask? So the question is, can I repeat the content of exam 3? And my answer to that is you can watch the video, or I'll hope to post it by tonight. Okay, so I'm not going to go over the whole thing again, but suffice to say, just sort of where it makes sense to stop. Okay, so we were almost done talking about implementations of abstract data type stack. The fundamental functions associated with the ADT were push and pop. We also give the client the ability to check for emptiness, and that's kind of laziness on our part, but we're gonna have that be the interface for this class. But there was one dangling issue. Now, I assert that over the last couple weeks, this has been a minor source of anxiety for many of you. And that source of anxiety, I think, is tied up in using arrays to implement some of these abstract data types. It came up when we used an array to implement a list, and it came up when we used an array to implement a stack. And that source of anxiety is, what if the array fills? What strategy do we deploy? Do we quit and go home? Do we, what do we do? Quit and go home is a popular option. It's kind of what we've done up until this point, but I want to give us another alternative. Now, the screen wanted to quit and go home. Wake up. Really? Uh-oh. Uh-oh. Nothing. I got nothing. Oh, I got something. Oh, man. Connect. Boy. Sorry about this. I have hope. I have hope. Okay, we're back. Okay, so the issue then is what do we do if the array fills? So here's what I would like to propose as a general idea. Okay, we're going to take advantage of the location, the available space in the array, and we're going to let it fill and not worry at all until another piece of data comes along. Okay? Now, when that other piece of data comes along, we're going to do the following two things. We're going to create a new, bigger array. Oh, three things, actually. Create a new, bigger array and copy the existing data into that array, like this. And then we're going to insert the new piece of data that came along. Okay? Any question about that at all? Now, there's a part of that that should still bug you to death. What part of it do you not like? Yeah, Bart? Oh, what about the old array? Oh, very good, good. Maybe there are two parts that should bug you to death. After we've made the copy, we're going to go ahead and give back the old array to the system to use, okay? Good observation. What else bugs you about this? What else bugs you? Yeah? Ah, very good. This is a good observation. Look, if we deploy this scheme, for just a second, we're using this array and this array at the same time. So we can kind of observe that this process demands twice as much memory as the amount of data that we have. And we're going to kind of let that be true. We're not really going to address that issue very carefully in this class. Did you have something that was bugging you too? This part of it? Yeah. So that's the part that really bugs me too. That moving the data, copying the data from one array to the other, that feels like wasted time, right? Do you have a question? It depends what you've got in there. If they are objects, then they will have to copy them, right? They have to inhabit different memory. If they're pointers, then, it's maybe not so expensive, but they might not be pointers. We're not going to try to control that. Yeah?
What about the scope of the second array?
The scope of the second array is going to be exactly the same as the first. In fact, from the code's perspective, after you're done with this mechanism, that second array will be the first array. It'll replace the first array. Okay? Does that make sense? Okay, any other observations? Yeah?
Well, we have an array of size 4.
Yeah?
Size 6.
Yeah. Okay. Are you saying why?
No, I'm just
Yeah. Yep. Yeah. All right. So the observation is that I had an array of size 4, and I created an array of size 6. Now, that first location is kind of spoken for, right? But the second location there, well, that's a freebie. That means the next piece of data that comes along does not trigger any copying. I get to insert it basically for free, or basically for the amount of time that it would have taken anyway, okay? So that suggests that there is economy to be gained by not just making the array barely big enough, but by giving yourself some amount of nearly free future ads. Now the question is, how many nearly free future ads should you give yourself? Okay, that's in fact the question of the next 20 minutes or so. Any other observations or questions about this, this setup before we look at some math? Yeah? Yep. Yep. Can we address that question after we look at what to do to make it larger? Because really the answer is going to be, we're going to stand on our heads and pretend that making it larger is just like making it smaller, that making it smaller is kind of the inverse of making it larger, okay? So that's a great question for 20 minutes from now, approximately, if I'm optimistic. Okay, so we're going to look at two different schemes for giving ourselves some free future ads. Here is the first one. Shh. Here's the first one. We're going to say that the amount by which we increase the array is always some constant value, any constant value. Here, I have made that constant equal to 2, right? Every time I increase the size of this array, I bought myself only one free future ad. The current one is free and one free future one. But you can imagine that this constant is 50 if you like, or 500, or 1,000, who knows, right? So you can imagine that it is just some fixed number that you might choose relative to the actual architecture on the machine. Who knows? Later on, we'll see a case where that's definitely true. Okay, so any question about the setup? I'm going to parameterize this starting from 0 here. So I'm going to pretend that we start with an array of size 0. I don't know why I didn't really have to, but and that the first data element that comes along induces a creation of one that is 0 plus 2 more, okay? So this one is already the first, sort of the first version of it, the increased version of it, okay? So now let's look at what happens here. We are going to accept a 3. We're going to accept a 4 into our new structure. The second a 6 comes along, we're going to make a copy of the 3 and the 4, insert the 6. Then a 2 comes along and we've got a spot for it. If a 9 comes along, say, we need to copy each of these. Then insert the 9 and then we've got the blank spot. Now, we could continue this discussion arbitrarily long. And the way I'm going to describe that is to say that we're going to look at the overall cost of this for n data elements. So for assuming that we're going to put into this structure n elements, okay? Happens to be pushes because we're talking about a stack, but it could be inserts of various kinds, okay? All right, and for simplicity and clarity, we are going to assume that C divides n, which is another way of writing there is some integer k so that n equals C times k. Okay, that's those two things mean the same thing. Or you could also say the modulus is 0. N mod C is 0. Any of those, same story. And that's just for simplicity of argument and to avoid floors and ceilings and things like this. We're only going to take a peek at our analysis when our arbitrary value is a multiple of C. Okay, so I'm going to draw a few more arrows on this picture. Okay, these are arrows. And I'm going to observe the following. It's really only the arrows that constitute what feels like unnecessary wait time or extra waiting time. all of the process of inserting the data to begin with, the first time the data goes in, you're going to incur that cost no matter what. No matter where you're putting the data, you have to just sort of absorb the cost of putting it into the structure. So my analysis is going to focus only on the additional cost of waiting for the copying to take place. Is that all right with you? And then all I'm going to do, essentially, is look at my picture and go, all I really have to do is count arrows. Count arrows. Well, even that is easy. In this row, I've got 1C, number of arrows. In this row, I've got 2C arrows, right? In this one, I've got 3C. And basically, I just need to add all those up till the very end. And that will be my total cost of doing this. Now, for my first go at this, I'm going to parameterize my running time by K instead of by N, because it's easy. Because evaluating my running time is really easy if I just look at each of these copying events independently. Okay? All right, so now this is like 0 C's plus 1C plus 2C plus all the way up to how many C's? Whisper it to the person sitting next to you. So what I'm listening for when I listen is the sound for the s, because when you say K minus 1, when you say K minus 1, it's the s that travels, right? I knew you were all going to say K something. And I would know that if you said minus 1, I would be able to hear it. And I did hear it a little bit. So this is, in fact, K minus 1 copies of C. Because these last two, that last copy of C is going to be the one that fills it up for the next time. It's what induces the next copy. Okay? All right, well, I don't know about you, but I really would prefer to write this like C. I'm going to factor the C and write this as a sum that might trigger a memory. So I equals, okay, 0 to K minus 1. It could be 1 to K minus 1, whatever, of I. So right here, you guys should all look at this and go, oh, yeah, I got that. Okay? That's what I think of as a back pocket sum. You have an opportunity, if you're at a dinner party or whatever, to impress the people around you by being able to say, oh yeah, that's just every time. If that's not true for you yet, write down this sum after I write down the end of it and put it on the bezel of your computer, okay? So that you see it so often that it becomes part of your knowledge, sort of like the times tables. We've grown up from the times tables, okay? All right, so somebody who has already put it on the bezel of their machine, want to tell me what it is? Here? You ready? Yeah, Neil? So he said n times n minus 1 over 2, and he's darn close. Thank you. Yeah, I see no n. There are no n's. I don't know what n is. In this case, it's k. So it is the upper bound plus 1, which in this case is k, times k minus 1 over 2, and then we have this factor of c sitting out front. Okay? All right. Now, nobody in your world is ever going to want a running time reported in some little parameter that you make up relative to the problem. So what you have to do Once you've got this simple analysis here, what you have to do is change it back into the parameter that denotes the size of your data. That's how people want to hear the report of the running time. So I'm looking at this right here, those two terms together, and what do I see? What is that? What is C times K? N, right? So the modification of this is, it's actually a composition, but C times K is N. And then I don't like my K's, so I'm going to write this as N over C minus 1, and then it's the whole thing over 2. UG fractions, but all the fractions have constant denominators, constant coefficients. All of the values of N have constant coefficients. So if I'm going to do this, what am I going to put in the parentheses? What do you see? What's the degree of the polynomial here? N squared, very good. The only significant terms are N squared. If that was too fast for you, you should go look at Margaret's notes for 173 and review the big O definition and arguments and give yourself some practice. The TLDR of it is, this is a messy looking version of a polynomial of degree 2. Okay? All right, so this is big O of N squared. Wait, backtrack. What's big O of N squared? Well, it's the amount of copying on a sequence of N pushes, because that's how much data we have. So this is the amount of weighting over a sequence of N pushes. So the cost on N pushes is big O of N squared. How does that feel right now? Is it okay? Does that feel good? No, anytime anybody comes to you with a quadratic algorithm, you go, that seems kind of expensive, okay? And you start thinking about ways of improving it. I'm going to change the results slightly here because I don't want the evaluation over a sequence of N pushes. I want it for a single push. I want to evaluate the cost of a single push. Now, I can't do that in this case because lots of them are really super fast, right? It's just occasionally we have to wait for the copy. So the way I'm going to state this for this class is on average, we have big O of N squared over N equals big O of N per push. Okay? Now again, sometimes super fast, but sometimes you have to wait. If you take all those experiences and you add them up and divide by the N, the total number of events, on average, you will have weighted big O of N per insert into the structure. Is this good news or bad news? Good news or bad news? Yeah, do this if it's good news, this if you have no idea, and this if it's bad news. If you're not doing something, I'm going to assume this, okay? Wait, no, I'm going to assume this case, okay? All right, this is really bad news because think about it. This is the cost of shifting. Every time you make a change, right? This is the cost of shifting. This is the cost of finding in linked lists. This is something that per event, we don't have time for. We don't want to incur a huge cost on average per data element. We don't want to. We We could do that just with a linked list here, okay? All right, so this is bad news. It's not what we're looking for. All right, so let's see if we can do better. Take a look at this scheme, and somebody raise their hand and describe for me what I'm doing here. Yeah? Yeah, that's right. Every time you make a copy, you make the new one twice as big. Have you seen this before? Have you done this before? Binary search. Did we ask you to do this scheme for MP2? For increasing the size? Maybe we didn't. I don't know. Okay, never mind. All right, so here's the idea. Here's the idea. We're going to start this time. We're going to start this time with a single piece of data, and then we're going to copy that. Right? That gets us one free ad. And then if another piece of data comes along, we're going to double the size of the array and copy the data again, just like before. Insert our new one, and it gets us this one free ad. Right? Then we're going to copy again. And we start to see the advantages. Look, this time we get 3 essentially free adds to the structure. Just like last time, I'm interested in these copying events. The actual additions to the structure, just like last time, they occur anyway, right? We're putting something into an array. That doesn't cost us more time than we anticipate. It's the waiting. It's the waiting that kills you, right? All right, so now the question is, how much waiting am I doing every time? This one is, well, all right, fine. T of, something. The running time is, I'm just going to leave it like this for a second. 1 plus 2 plus what? 2 squared plus 2 to the third, right? Right. Oh, I forgot to say, this time we're going to assume that n is a power of 2. Okay, so similarly to last time, we're choosing to look at our arbitrary data size value when it's a power of 2, so as to simplify our argument. We could use floors and ceilings to do the analysis more robustly, but there's no reason to do that, okay? So we're going to pretend that n is a power of 2, and then my question is, how many of these copying events are going to happen? That is, what is the size of this last one? Plus 2 to the 2 to the k? Half of 2 to the k, right? We're only going to copy half of 2 to the k, so what does that mean? 2 to the k minus 1, good. So this is all the way up to 2 to the k minus 1. So in terms of k, where k is this, this thing that we're using to parameterize n, to describe n, we've got the sum from I equals 0 to k minus 1 again of 2 to the I. Oh, look, another back pocket sum, right? If this one isn't immediately known to you, you should write it down, put it on your bezel. I'm telling you, you never know when it's going to pop. The knowledge is going to be impressive to somebody. Okay, I'm ready for it. Who knows it? Yeah? Oh, like this? 2 to the k minus 1, like that? Yeah, right, good. I always do them over 2 minus 1 in my head too, because then you can generalize it. But yes, exactly. Any question about it? Okay, fine. Are we done here? This is a slightly different thing. It's not really a different function. What is it? What is it? So what is it? N minus 1, right. So over the sequence of n pushes, that n could be 25 gazillion, okay? That n could be a really big n. And in the end, the amount of time we spend waiting, just the same, right? The same. It's proportional to the size of the data. So this is n minus 1 because 2 to the k equals n, okay? All right, so let's see. How does this scheme do on a sequence of n pushes? Well, this is big O of n. So on average, this is big O of n divided by n, or constant per push. Yay! Because all that means is that each one of those inserts that was going to happen anyway, you, in the analysis, you pretend like they just, each one of them just cost a little bit more. In the algorithms class, you will do a bunch of problems like this, where the strategy for solving them is called amortized analysis instead of average analysis. And the only reason for that is because average in that context means something different. Okay, so you average over a different probability space. So this is essentially the same as amortized analysis. And the idea is just what I said before. You have very frequent, very fast operations, and sometimes you have to wait. The question is, how, over the whole course of the algorithm, how much time do you have to wait relative to the size of your structure? In this case, look, not much is the answer. So this is a really nice result. I'm going to put it in green. Yay! Okay. There was a question. So any questions about this, first of all? About this analysis, about the argument? Okay? So the question is, how do you really implement it? The question that I have here is, how would this look if you really implemented it? And the answer is, you know already. You're going to, I'm trying to think if there's any place where we ask you to do it. Oh, it's very much like what you do for MP2. It really is. You allocate space for a new array, copy the data one by one, insert the old one, change the capacity, and free up the old space. So the ideas here are not different from what we've seen before. Okay? Let's see. Anything else? Any other questions about this? So there was a question asked earlier that I want to readdress. I don't remember who asked it. It might have been, did you ask the question? Can you ask your question again? Oh, darn it. Imagine this. So we're doing this with a stack, right? So imagine this. We insert a ton of data. We insert a ton of, so that I'm pretending like the bottom of the stack is here. I'm inserting a ton of data. Push in a whole bunch of data, right? My use case says do this. And then for whatever reason, we end up popping a bunch. Okay, popping a bunch of them. And then imagine that we just have a bunch of pushes and pops here, right? There's nothing in what we've discussed that talks about freeing up any of that memory. What do you think we should do? What do you think we should do? Yeah? Very good, very good. So the suggestion, and it's actually the intuitive suggestion, but there's a huge problem with it. There's a huge problem with it. The suggestion is when the array is half full, then you shrink it, okay? And the substance of the suggestion is great. The detail has an issue. And I see some of you going like this. Okay, so what's the problem with that suggestion as it is? So the suggestion is that when the data shrinks to about here, you shrink it by half. That is, you go back to this story. What's the problem? Yeah? Yeah, look, the very next thing that happens is you're going to make it bigger again, right? And so there is this chance that you're going to be going back and forth, making it bigger, making it smaller every time. So what you do is first of all, you let your trigger be a smaller fraction, say a fourth, and then you shrink to a half so that on average your array is always no more than or no less than 1/4 full. Okay. Now, what does the analysis of this look like? So first of all, I'm not going to test you on the analysis of this. Okay, I don't think we've done it as carefully. Right now, this is an intuition kind of discussion. But what does the analysis look like? Well, you kind of turn your head upside down and you look at that picture. This slide, if I were making the details of the discussion for removing, I'd turn it upside down, right? It's the very same thing. And we'd look at the costs of the shrinking, the dividing in half each time. All right, and our result would be the same. We'd end up with constant time, in this case, per removal. All right, any question about that? Again, if it were something whose details I was going to test you on, it would have its own slide. It's only the intuition here that's important. Okay, so what would change in my analysis if instead of doubling the array, I would triple the array? What would change in my analysis? What would change in the scenario if I k-tupled it? I don't know. If I multiplied it by some other constant, what would change? Yeah? Yeah, in the analysis, the base of the exponent would change, and everything else would fall out the same. K would be log base 3 if we were tripling it, say. Okay, and so the punchline would be exactly the same. So what's the problem with, say, tripling it? Yeah? Excuse me? Yeah, you lose some space efficiency, right? We're using 3 times as much memory as we might need rather than twice as much memory as we might need. Now, okay, then why not 1.5 times? Okay, you see, if you wanted to ask that question, you see all the issues. We're just discussing 2, okay? You could figure out the others now. And probably in 374, you will do a little bit more analysis here. Okay, so I want to pull it all together in the context of stacks. Yeah?
What is this considered the most efficient way?
So what happens is you have to address so the question is, what is this the most efficient way? And the answer is, at that point, you have to address the trade-offs. Maybe you have unlimited memory, in which case maybe you should use 100,000, right, for the base. But if you don't, if memory is one of the constraints, then you want to look smaller. So the function of the trade-off, number one, changes with the architecture of the machine and the hardware available to you, but the analytics stays pretty close to the same. It's just what constants this big O is hiding that change. So for this class, The answer is you double the size of the array, okay? But there's a deeper understanding that goes along with it. How about that? Is that okay? Okay. Let's see. Any other questions about this? I forgot to say something at the very start. It was on the slide, but I forgot to hammer it home. And that is, we have now calmed ourselves about the issue of an array filling for a stack. But we haven't talked about the array filling for a list, or later on, maybe even today, we're going to talk about queues. Later in the semester, we're going to talk about several different abstract data types that deploy an array. This analysis applies to all of them. So from this moment forward, we're never again going to worry about arrays filling up. We're going to agree to understand that when an array fills up, no big deal. You just double the size and copy the data, okay? Now, hidden behind the standard template library vector, this is done, right? The implementation of the vector includes this functionality, as well as all the linear structures. All the linear structures will have this functionality. All right, that said, let's revisit stacks. So we talked initially about implementing a stack with a linked list, and we agreed that we had constant time push and pop at the head of the list. Now, I think you should think about the consequences of, say, how do the running times change if instead of doing the pushes and pops at the front of the list, you do it at the tail of the list instead? Does it help to have a tail pointer? All of those questions I kind of would like for you to address in your own cogitation. If you're having a hard time falling asleep at night, think about it. You'll fall asleep quick. All right, so, but for our purposes in this moment, we've argued that using a singly linked list, where all the action happens at the head of the list, we have constant time push and pop, okay? Now, let's summarize what we know about using arrays to implement stacks. Well, we get constant time pop always, and if we're more clever about resizing, then it's constant time pop on average, okay? But for now, we weren't careful with the amount of memory that we use here. So we'll just say it's constant time pop. And there's constant time push if the capacity exists. And the cost over n pushes, where sometimes we have to wait, is only linear time. And the average of that is constant time. Now take a look at this. Without qualification, with no hemming and hawing whatsoever, we could make this statement. But using an array for a stack required all of this, well, on average, it required all of this sort of supplemental discussion. And moreover, it's only an average result. Sometimes you really have to wait. So the question on the floor is, why use arrays at all here? I wondered that the first semester I taught this class, okay? I really honestly wondered it. I didn't just know. And so I went off and I implemented this thing. I implemented a stack using an array and using a linked list, and then I hammered on it. I built the structure out to 1 million data elements. I shrunk it. I really tried to incur the worst cost behavior of both the linked memory, the stack implemented with linked memory, and the stack implemented with an array. Guess which one was faster? Including resizing. Everything I did to it, which included a lot of resizing. Guess which one was faster? Raise your hand if you think the linked list. It's always constant time. Raise your hand if you think the array. Yeah, good. I wouldn't be telling the story otherwise, right? And now what I want you to do is, again, using your fingers, tell me the factor of speed up. That is, if you think the array was twice as fast, hold up 2. If you think the array was the same speed, and you don't know why we're having this discussion, do this. If you think it was 5 times as fast, do this. Show me. It's a guess. It's a guess. Twice as fast. I'm seeing a lot of these, How did you know? Seriously, how did you know? You guessed? Okay, here. Yeah, it was 10 times as fast. I don't know why 10, but I tried. I tried really hard to give the linked list all of the advantage. And it was persistently, for lots of different sizes, 10 times as fast to do this with an array. Now, I really do know why that's true. It's because arrays are stored in contiguous blocks of memory, and that's how the pages are loaded into the cache. Okay, so that's how the data is loaded into the cache. So the fact that the arrays are faster has to do with the way the hardware is built, the way the way the processor manages your data. So here, it's 10 times faster by empirical study. Okay. All right. Any questions about that? Okay. So we're going to switch gears. We're kind of done with stacks. We'll be using stacks. MP4 uses stacks, and this week's lab uses stacks. Every data structure book ever written has a chapter entitled Stacks and Queues. That's right. Has a chapter entitled Stacks and Queues. And that is our next abstract data type. Okay? No. We're not done. No. We're not done. We have 4 minutes. We can do an amazing amount of stuff in 4 minutes. The reason they're in the same chapter is because a queue is also a constrained access linear structure. Okay? For a stack, the constrained access, that is, both the entry and the exit to the structure is on one end. In fact, there is a kind of mnemonic that we use for stacks called a LIFO. We call stacks a LIFO ordering structure, where LIFO stands for last in, first out. Okay? Queues, on the other hand, have an entry to the structure that we refer to as the rear and an exit from the structure that we refer to as the front. Now, this is totally consistent with our cultural understanding of a queue. If you are at the front, you will be the next to leave. This is the lines at Disneyland, kind of. This is the Chara queue, right? This is the line to get in the room when you pick up a handout. This is the dining hall line for hot food. It's pretty much every line you ever stand in, unless you've got good elbows or a friend in the second position. Okay, and moreover, queues are used internally to many software systems to orchestrate the processing of events. We're going to see queues used in a lot of our algorithms even for precisely that purpose, to order the events in a way that is kind of this, well, it is the first in, first out, first come, first serve process. So this is a FIFO ordering structure, where this is first in, first out. The only reason I bring that up is because you're going to hear it, and because one of the purposes of the reason I bring it up is because I'm actually kind of confused by it, because it's just a culture, it's a matter of culture that says we call it first in, first out instead of LILO, right? Last in, last out. And this one could be philo, and it's the same, first in, last out, right? It's the same. So it's really purely cultural. So there's one more issue, and that is Why do we have these constrained access structures? Why are we constraining the access? We're doing the users of our class, the reason is we're doing the users of our class a favor by providing them only the functionality that they need. So if there is an application that only needs the first and the last of a structure ever, then we're going to give them a queue. If it only needs the top, we're going to give them a stack. If it needs random access, we're going to give them a list. So we do this just to help the clients. All right. Bye.